Yeah, hello everyone. It's our pleasure to have Casper to present his work in our seminars, and today's he'll be telling us how to configure our quantum machine learning model through the lens of structural risk minimizations. Yeah, literally just read out from his title. And Casper, this floor is yours. Casper, we can't hear you.
Does it work now?
Yes, yeah, it works now.
It's the weirdest bug on Zoom. I'm very sorry for that. It always happens.
No worries.
When the recording starts, I have to open up settings again and press one button and then it starts working. Okay.
Right.
So let me just go full screen here. So everybody hears me now?
Yes.
Perfect. Okay. So again, thanks for having me, but not to everybody. I'm indeed going to talk about structural risk minimization and sort of what lessons we can learn from this paradigm if we look at our quantum machine learning models through the lens of linear models. Basically, that's what this paper is about. In terms of structural risk minimization, which I'll explain what that paradigm is, what can we learn from it in terms of quantum machine learning models if we draw lessons from linear classifiers. So just first, let's sort of look at what kind of machine learning models we'll be looking at today. Many of the machine learning models that currently are proposed look as follows. They have an encoding circuit, sometimes called feature circuit, sometimes called embedding circuit, which takes a classical data point x, say a real number or a real vector. It feeds it as parameters into some parameterized quantum circuit. This is applied to the all-zero state, and out we get a state that in some way depends on x, which I'll throughout this talk denote rho of x. And on this state rho of x, we're going to estimate an expectation value of some observable O. And if the expectation value of the observable O is larger than some threshold D, we assign it label +1. We say this data X was a dog. And if it is less than D, we assign it label -1. We say it was a cat. And today we're looking at mostly at the observable part of this. Where there will be some lessons on the feature encoding, but the lessons that we learn are basically what kind of observables do we look at. And the way these observables are implemented, they can be done in many different ways, or at least the most two well-known ways are either using a variational circuit, where you train a circuit afterwards using gradient descent, and then measure some fixed observable. And if that threshold is larger than say D, then we apply +1, and if it's smaller, we apply -1. Or you can do a kernel method, which uses the feature states, and based on these feature states, it's going to construct an observable. And what do we mean by when we're training the model? We're basically finding the best observable O and threshold D. But these observables, since they're implemented in a certain way, come from a certain family, which in statistical learning theory is denoted as something which is called a hypothesis class or a concept class. In this case, it's really a hypothesis class, which is basically a bunch of functions, which the functions implementable by the model, which are these C, which are indexed by the observable O and the threshold D, which basically compute the sign of this trace. And this trace is nothing more than the expectation value minus D, which is basically the sign minus D is basically doing the thresholding. And depending on the model, depending on, say, the ansatz of your variational circuit, we're gonna have a different family of observables inside as our sort of possible candidates observable to separate the data points. And the question that sort of we tackle in this paper, or structural risk minimization tackles, is sort of what properties of these functions, of these observables, will make for a good machine learning classifier. Okay, but first, what do we mean by good, right? So good is very vague. So what makes a machine learning model good? Well, the main goal, or I'd say one of the goals, there's of course scenarios where you also care about fatal errors, but let's suppose our goal today is to minimize the expected generalization error. So the probability of misclassifying a randomly new drawn instance, or you could maybe have seen the instance again, but sort of it's just a random instance out of your data set. And what is the probability that my machine learning model will be wrong on this data point? Well, let's say it is a cat if it's actually a dog. And statistical learning theory sort of tackles this question by looking at a certain range, a family of generalization bounds, which tells you that this generalization error on the left-hand side, which is the quantity we try to minimize, that's the goal of today, minimizing the quantity on the left-hand side, is upper bounded by the training error, plus something which is a function g that depends on both the training data, say the magnitude of it, but also something which is called the complexity, or a complexity measure of the family of functions, of the family of hypotheses. It's sometimes called capacity measure, it's sometimes called complexity measure. And one of the more well-known examples is VC dimension. Today, we're going to discuss VC dimension plus one more. And the idea of structural risk minimization is to use this bound. But right away, we notice, or at least not right away, when we look at it, we see that, these terms are counteractive. I don't know how to say this. So if the training error goes down, that means that, if the complexity goes up, then the training error typically goes down. So it's like a balancing of the two. And if you have to draw like a picture of this, we see that the red line is exactly the bound on the right-hand side that we try to minimize. Right? If we minimize the right-hand side because of the inequality, we also minimize the left-hand side. And we see that sort of a balancing act. We see that we want to increase the complexity in order to obtain good training errors, but we don't want to increase the complexity too much. We want to find this sweet spot. Sort of a word that sort of arises here a lot is like overfitting, right? So you don't want to make your model too general, too complex as to overfit on the training data, because in that case, you're here. I don't know if you see my mouse. Is my mouse visible? Okay. On that point, you're here. You want it to be just complex enough to sort of capture the correlations in the data, but not too much. You want to balance it. And this is a paradigm in machine learning. It's like a 90s style mathematical machine learning idea on how to train or how to select your models. With the success of neural networks, people have started to discuss whether statistical learning theory really is the main answer to what makes a good machine learning model. But today, the idea of the paper was, well, suppose we want to do structural risk minimization. Suppose you are a believer. How would I do this for our quantum models that I discussed in the previous slide? So the main thing here, the main idea of the research here is, can we identify tunable properties? So something that we can have a handle on. In more machine learning terms, can we find hyperparameters in our model that we can prove moves us basically along the x-axis of this plot here? Can we find parameters? Can we find properties, hyperparameters, something in our model which helps us sort of slide from left to right on this x-axis in order to perform, let's say, the balancing act in structural risk minimization? And for that, we took a look at two complexity measures. One, as I mentioned, is perhaps the most famous one, the Vapnik-Chernoff dimension. No, not Chernoff, Vapnik-Chapnik dimension. Well, no, I forgot. I should have known. And it's basically, it's given by the size of the largest set of points that your model can shatter. And what do I mean by shatter? It's correctly classified under all possible labels. So for instance, if we look at linear classifiers, which try to draw a line between points to separate them, we see that if we're looking at two-dimensional classifiers, its VC dimension is equal to 3. Because 3 points, no matter how they lie, no matter what labels I give them, I can always draw a hyperplane that separates the pluses from the minus. However, there's the very famous SOR dataset, which is the 4 points on the right, which you cannot classify using a two-dimensional linear classifier. There is no way to draw a hyperplane between these 4 points such that I separate the pluses from the minus. So that's VC dimension. It's a way to sort of characterize what the capacity, what the complexity of your model is. And the generalization bounds that I discussed on the previous slide heavily depend on this quantity, or at least one of the generalization bounds that look like that. And on the other hand, which I've also studied in the paper, we've also studied in the paper, is the fat shattering dimension, which is, it's like the VC dimension, but it's a bit different because you also take into account the margin with which you separate the pluses from the minus. So it's really the size of the largest set of points that your model can shatter while also attaining a certain margin. And by margin, you should really think about how close are my data points to the decision boundary, which in linear classification looks like this, which is basically this distance gamma from your hyperplane. Sorry, I'm pointing with my finger. This distance gamma from the hyperplane to the data point. Really, this is the margin. So it's like a generalization of VC dimension. And what we went ahead and did in our paper is our goal was to sort of identify tunable properties which allowed us to control this VC and fetch chattering dimension. Because as we said on the previous slide, it helps us navigate alongside the x-axis in structural risk minimization.
Sorry, Casper, I have questions over here.
Of course.
So what motivated you to use these two complexity measures instead of, for example, the Rademacher complexity?
Okay, so Rademacher complexity is closely related firstly, and I think they're sort of there is a sort of a bound that sandwiches them, if I'm not mistaken. But for me, the main motivation here is we, as we will make clear later in the slides, is that it's a known fact, or it's at least that the models implemented by quantum machine learning models are linear classifiers.
Mm-hmm.
And the two complexity measures that have been widely used to study the behavior and to study, say, support vector machines to explain why we want to do maximum margin stuff were the VC dimension and fetch chattering dimension. So these were, say, also highly used in the classical literature, is, I would say, sort of the point why I chose these. They were highly used in the classical literature for linear models. And let's see, quantum models are linear models, but they're a different kind of linear models. What do these complexity measures say about these kinds of linear models? That was the main reason.
I see. Okay. Yeah. Fair enough. Yeah. Sorry. Yeah. Continue. Thanks.
Oh, but I'm not saying they're the best. I'm just saying we.
No, of course. As in, like, the reason why I'm asking because I'm using the Rademacher complexity for my studies. Yeah. So I'm just wondering, like, why you choose these two instead of the one that I use. Yeah.
Yeah, inspired by classical literature. I'm not saying they're the best. There's so many out there, from covering number to Rademacher complexity. After these two were designed, there was much more designed, more aimed at explaining the success of neural networks, which there's less of a link, I'd say, between neural networks and machine learning models, more to linear classifiers and machine learning models. So I wanted to exploit that link, let's say.
Right. Okay. Yeah.
Okay. So now that we've seen the complexity measures, let's think a little bit about what sort of the results were we attained. So I'll first give you the theoretical results, and then later I'll sort of draw lessons from it, at least the lessons that we drew. Everybody can draw their own lessons from the theory, but this is sort of how we interpreted the results. So the proposition of VC dimension here, in terms of what the VC dimension of a quantum machine learning model looks like, we let O be a set of observables. So let's suppose this O is all observables implementable by your variational quantum circuit. Or let this O be any model be any observable implementable with a kernel method that uses a certain feature map. And we're going to define a quantity R. A quantity R is the dimension of the sum, so not direct sum, really the sum, where in direct sum you're sort of subtracting overlap, in sum you don't do that, of the images of the observables inside my family. And this quantity R, when I square it, is an upper bound on the VC dimension. So what do we see? We are able to control the VC dimension by carefully looking at R and ways to limit it. In the next two slides, we'll explain sort of, look into how to do this in practice. So really looking at your variational ansatz and your observable, how can I play around with these ingredients such that I'm able to control the quantity R? But at least from the VC dimension case, it's important to look at the dimension of the images and make sure that basically this linear space on which observables act isn't too high dimensional. At least you want it to be high dimensional enough for training error to be sufficiently low, but not too high for overfitting to occur, according to the structural risk minimization upper bounds. And in terms of fetch chattering dimension, we identify a different quantity. This is not the ranks, let's say, or the dimension of the images, but really the Frobenius law. So we again let O be a set of observables implementable by your favorite quantum machine learning model. and we let eta be the max Frobenius norm of the observables in the family. And then we see that the fetch-shattering dimension, so the total number of points that I can shatter with a margin gamma, is less than or equal than something which goes quadratically in the Frobenius norm and divided by the gamma, which is a function of gamma. But the thing that we can control here in the model is this VC dimension. So from the structural risk minimization perspective, we want this Frobenius norm to be large enough to attain low training errors, but not too large as to cause overfitting according to the generalization bounds related to structural risk minimization. So quickly sketching the proof, how do we get there? As I mentioned before, the classifiers are of this form, which is sign trace O rho, which is basically the expectation value minus D. And we notice that this trace is the same as something which is called the Frobenius inner product in the space of Hermitian matrices. In other words, all we're doing is we're implementing linear classifiers in the space of Hermitian operators, where the hyperplanes are given by the observables, and the points which I'm trying to classify are given by these density matrices which encode the data. And we know that they're inside the unit sphere because of the fact that they have to be a mixed state, which have trace equal to 1. So if we combine this and we look at bounds on the complexity of linear classifiers, so we plug in the right space, we plug in the right norms of the data points, we plug in the right hyperplanes, and we find that we're able to obtain the above propositions. Okay, so now we've quantified, or at least we've established some bounds, say, on the complexity of your model, depending on these two qualities. But what about the training error? Can we also sort of quantify that they really have an influence on the training error? Because these are just bounds, right? So these are just upper bounds. They can be, I don't know, very big and not really tell you about the training error. So can we also prove sort of the other side of the coin? We now know that the complexity line in the structural risk minimization goes up, but does training error also go down if I move along these two quantities? And to answer this question, we also have two propositions. And like I mentioned, I don't think I mentioned, at least like we'll see later, is that this quantity R can be limited if you design your model in the right way by limiting the rank of the observables. So the question here is, what does rank have to do with training error? And what we were able to show is that increasing the rank of the observables strictly increases the model's capability to achieve small training errors. Very vague term, but what do I actually mean? We mean that any data set that can be classified by a certain rank can also be correctly classified by a larger rank, by a strictly larger rank. So notice that I'm not sort of cheating with a smaller equal, now really a strictly larger rank. So you're not losing expressivity by increasing the rank. And there exists data set which really require you to have at least a certain rank of observable. So how does the proof go? Again, I'm going to sketch it a bit. What we were able to do is we were sort of able to construct a tomography protocol, which allows you to query the observable, the classifier. So really, you're just getting pluses and minus ones. You're not getting raw expectation values. You're not getting any other information. You're just getting, does my classifier say +1 or -1 to this data point? And by interpolating between where it sort of changes sign, we were able to find a protocol such that if two observables output the same labels during this protocol, then the eigenvalues must be pointwise close. And if the eigenvalues are pointwise close, you know a few of them are 0, then they must also be 0 on the other hand, which tells you basically about the rank. So two observables of different ranks will not output the same labels during the tomography protocol. So the data set of points queried during the protocol will give you a data set where they have to disagree on. On the other hand, we have rank for VC dimension, and we had Frobenius norm for fetch-shattering dimension. And what we noticed is that increasing the Frobenius norm also strictly increases the model's capability to achieve large margins. Again, this is the informal statement. What do we say? We say that there exist data sets which only observables of Frobenius norm larger than some eta can achieve a certain margin, comma star. So how does this look? It's a very simple data set. It's basically the data set of computational basis states, but this time as written as mixed states, where half of them, let's say the first half, we assign label +1, and the other half we assign labels -1. And first we note that there indeed exists an observable that is able to classify this data set while attaining a certain margin. And the observable has Frobenius norm eta, and it achieves margin eta divided by square root m, where m is the magnitude of my training set. And on the other hand, we saw that if there's an observable which has a Frobenius norm which is strictly less than eta, and let's suppose it achieves a certain margin gamma, under these assumptions, by an application of the Cauchy-Schwarz inequality, we find that the margin that it attains has to be less than eta over square root of m. So in other words, if you really want to classify this data set, you need to be this observable with margin. If you really want to classify this data set with margin and eta divided by square root m, you need to have a Frobenius norm eta. Otherwise, you will not be able to classify this. So again, we saw previously that the complexity indeed increases with this quantity r and the quantity eta, which is the maximal Frobenius norm. But now also we see that training error indeed goes down strictly when I'm increasing the eta and the r. So this is like the second curve in structural risk minimization. So in the end, this quantity r and this quantity eta are tunable properties, or at least their properties, and I'll later show you how to tune them, of observables that can help you balance the model's complexity and training error. So if you believe in structural risk minimization, if you believe this is the thing that's going to sort of increase the performance by my model, maybe you're using other different techniques as well, but suppose you want to sprinkle in a little bit of structural risk minimization, then one way of doing it is by really looking at this quantity r and seeing if you can design your model such that your quantity r is limited or how it behaves, basically. And if you can identify properties that help you sort of tune r and tune eta. So how does this look in practice? In practice, we have the following, which is typically done. Instead of minimizing just the loss function, we regularize the loss function. So we train both we minimize both the loss function, and we add a second function h, which is a function that penalizes parameters omega, where omega are just some hyperparameters of your model, corresponding to a higher complexity. And now suppose we want to do this for our models. Suppose we want to successfully or sensibly regularize our training procedure, where again, note that this first term corresponds to this term, and the second this first term corresponds to this line here, the training error, and this one corresponds to this. And by minimizing them both simultaneously, we hope to hit the sweet spot. Basically, we hope to hit where they're sort of both, the smallest. At least their sum is, let's say, their sum is the smallest. So the goal here is now we have our bounds, we have our r, which is this quantity that influences the VC dimension. We have this eta, which is the quantity that influences fetch-entering dimension. How can we identify sensible functions h that allow us to do structural risk minimization? And for this, we're going to have a closer look at the two specific models that are used in practice, namely the kernel model and the variational model. Okay, let's remind ourselves what the VC dimension bound was. It's this r squared plus 1, where r is this dimension of the images of the observables. Okay, let's see what it looks like. Let's start with the kernel method. In the kernel method, the observables look as follows. Recall that these phi's were the encoding circuit. So these phi of x's are nothing more than the state you get by applying the encoding circuit with parameter x to the L0 state. And I'm writing it in density matrix form because we are doing linear classification in the space of Hermitian operators. And alphas are trainable weights that you get out of your training procedure. Typically, they are obtained by solving linear regression, but sometimes the data set is too big that linear regression is not feasible, and there's ways to do it differently. But we let alpha be free here. So in this case, we notice that R is the same as the span of your feature vectors. And notice here, by the way, that D is my training data. So this quantity R is the dimension of the span of the feature vectors, or at least the density matrix of the feature vectors. And there's not much to learn here in the implicit case, unfortunately. The interesting case is going to be the variational model. But at least if you want to learn here, and I think maybe there is a relation with Ben Yi's project here on merged kernels, is that you want to design your feature map in such a way that it's sort of confined to a smaller subspace of the reproducing kernel Hilbert space. That you don't want them to be all over the place. You don't want them to be orthogonal, because that's the worst you can do, in fact. Then there is no generalization happening at all. You want them to have an overlap, but you want them to have a certain overlap, not too much, because then everything gets mapped to the same point. That also makes no sense. But you also don't want them to be all over the place. There's a balancing act there. Something to learn. But the more interesting stuff happens in the variational classifier case, where the observables have this form. It's O of theta, where it's obtained by running a variational circuit U of theta, and then measuring a final observable, something fixed, something you don't train typically. Let's say for now we have it fixed. And the observables that you would get in this case, so this is just your standard quantum neural network, variational quantum classifier. I don't know what else people are calling it these days, but just sort of uploading, training a circuit and then measuring. That's what you get, these observables. And now we look at what R is. So it is the dimension of the span of all these observables. This is me just repeating it. There's nothing insightful here. But there's going to be some insight once we sort of start fixing the final observable. I'm just literally one-to-one copying what we have. It's the span of the observables that I get while I vary my variational parameter theta. But it turns out to have an interesting form, or at least an interesting lesson to be learned, when we let our final observable be a projection. And for now, let's say it's a projection on the first k eigenstates. Sorry, the first k computational basis states. And then something happens. We can rewrite the quantity R as follows. Now it is going to be the span of the first k columns of the unitary that corresponds to my variational quantum circuit while I vary the parameters. Okay, so now intuitively, you would say, well, if I limit k, my quantity R is going to go down. I'm using less vectors, so the span is going to be smaller, so R is going to be smaller. But this is not true for all parameterized quantum circuits. In fact, consider a very simple parameterized quantum circuit consisting of rotational X gates, one layer of it on every single qubit. For this one, the first column of the corresponding unitary already spans the entire Hilbert space when I vary the parameters. I can attain any computational basis state in that first column by selecting the right types of parameters, either on or off on the X gate. And therefore, this quantity R is already going to be exponentially large. So nothing is learned. So sort of what we get by this is that sort of a way to carefully design ansatzes. Design ansatzes in such a way that your columns, the columns of the matrices, span a low dimensional subspace when varying the parameter. You don't want it to go looking around the entire Hilbert space when I vary the parameters. You want it to be confined in a smaller space. And in the paper, we give 3 examples on this. And for instance, one of them uses symmetry preserving stuff, because we all know that the subspace of symmetric state is not exponential, sort of has a linear dimension in the qubit number instead of an exponential dimension. So if you, for instance, in some way are able to confine yourself to only work in this symmetric, symmetric subspace, which is the subspace of states where nothing changes if I sort of permute 2 subsystems of my 2 registers, then I'm going to know that my quantity R is going to be limited. So that's one of the ansatzes that followed. There's also some, let's say, ways to design your ansatzes such that it becomes a block matrix, and then being confined to one single block. Then you also know that you're only working in a small dimensional subspace. And we give 3 examples, more details in the papers, in the paper. Okay, so these were the lessons for the VC dimension. Now let's move on to the Havlíček dimension, which, as we recall, depends on the Frobenius norm. And let's again look at what this quantity looks like for both the quantum machine learning models. We again look at the implicit model, and we find here that the Frobenius norm is upper bounded by the one norm of the weights alpha that I use in my kernel. What this means is that this function h that we would like to find would be a good candidate for that, would simply be the one norm of the alphas, the weights that I use in my implicit quantum machine learning model. One thing to note here is, like I said, often this is trained by inverting a linear system and reading out the entries from there. And if you're doing it like this, then due to, say, Mercer's theorem, there's some mathematical body of literature, you already know that your weights are going to be optimally regularized with respect to the one norm, with respect to the Frobenius norm. This is something called the reproducing kernel, the representative theorem. That's the word I was looking for. However, like I said, in practice, the data sets are typically too large, so solving that linear system is not the way people would do it. And then sort of looking at the one norms would be the right way to do it. Finally, we have the explicit model, which takes, again, this form. And now we find that the Frobenius norm does not at all depend on the variational circuit. The variational circuit doesn't change the Frobenius norm. It's like it's a unitary matrix. So all the eigenvalues are norm 1. So nothing really happens there. However, it does depend on the final observable. And it turns out that, well, people have noticed, I don't think somebody explicitly wrote it down, but there is one way of implementing the variational quantum classifier where you run your variational circuit, measure in the computational basis state, you obtain a computational basis state, say bit string j, and this bit string j you feed through a neural network. And you average this process of measuring, feeding for neural networks, measuring, feeding for neural network, and you repeat this process a bunch of times, and effectively what you're implementing is the observable O final, where it's given by the diagonal matrices, where these lambdas are basically the output of the neural network. I'm using neural network just as an example, but any parameterized or trainable function would work here. So again, what you learn is that if your model is such that ansatz, measure, post-process, and average, then you must make sure that the post-process function doesn't have a large magnitude. You want this Frobenius norm, which is basically the sum of squared of the eigenvalues, to be small. So you want the post-processing of the measurement outcomes in order to train the eigenvalues, is sometimes what it is called. You say that the circuit trains the eigenvectors, and the post-processing neural network trains the eigenvalues. That's one way of sort of looking at sort of what happens if you implement that process. And you want these to be in magnitude not very large. Okay, I'm going a bit fast, but that's for me always the case with a Zoom talk. There's less interaction this way. So let me just hop to the conclusion slide, and then there will be plenty of time for questions, I believe. So the conclusion, we looked at a large family of quantum machine learning models, namely those that are that you can write as prepare, measure, and then threshold. In independent work by people have said that basically all models or I wouldn't say all, most quantum machine learning models can be put in this way, even with data re-uploading. I think it was even a former guest of yours that has shown this, Sofiane Gerbi. All these models are just prepare and measure. And we looked at them through the lens of structural risk minimization. We studied two widely known complexity measures inspired by classical literature that explained what makes a good very linear classifier, and at least popularized support vector machines, which are like, for people, the linear classifier, but there's of course literature behind it that tells you why support vector machines are the linear classifier. And these two complexity measures are the ones that we chose. We explicitly quantified how performance of training errors also behaves in terms of these bounds. And we studied sort of for these two specific models, the most well-known ones, what do we learn? What do we tune? What do we identify as being important properties of the model? And down the line, what this sort of gave us, which they have been called this before, observable-centric guidelines for designing new quantum machine learning models. So if your model is in terms of estimating expectation value of an observable, these are guidelines in order to help you what good properties of the observable are. There's a whole body of literature that focuses on the feature map, general Matthias Caro's work, and many other people have studied different complexity measures that the too long list to live up, but at least these will give you observable centric bounds from the perspective of structural risk minimization when viewing your model as a linear model. And again, so thank you for the invite and thank you for listening. I hope you enjoyed.
Yeah, thanks, Casper, for the very inspiring talk. I kind of learned a lot from your talks. Currently, we didn't have a question from the audience. Maybe I could ask some questions while people are thinking of what question to ask. So like over here, because like you are trying to control the complexities of the models by using two different parameters, right? One is like the Frobenius norm, the other one is the rank of your like observables, right? From your brain, you see that the Frobenius norm is quite easy to compute. Like for the implicit model, you just have to compute the one norm of the like parameters alphas. While for the second one, explicit model, you just have to like compute the like sum of like all the like function like lambdas that you have. But how about the rank? Is it easy to compute in your case?
No. So also there's no need to actually compute it. So okay, so where's the slide? Here. So there's no need to actually compute it. It's in this case at least. So if you're looking at variational models where your observable is sort of this sort of rank K projector, then it's basically just this number K that you want to be as small as possible while still attaining a large rank. Because you can show, as we see in the paper, as we explicitly say in the paper, that this quantity R is some function of K, or at least upper bounded by some function of K. So basically what you would have to limit is just K. There's nothing to compute besides that. You just you should write K here. And the unfortunate thing, it's not a differentiable function. So gradient descent isn't going to work well with that. It's more of a grid search over K, which isn't the most efficient thing, but you're at least trying to make K as large such that you have good training errors, but not too large to overfit. And it's really about this quantity K here, the rank of the final observable. If your ansatz is tuned in such a way that it indeed influences R, but you need a special ansatz for that.
Right. So like in this case, basically you will treat K as your hyperparameters and use all the like techniques in the classical literature to choose this K, for example, the n-fold validations techniques and stuff like that.
Correct. Yes. Right. Find the K which has best cross-validation performance, something like this. Yes, it is. And that's a very good word. K is the hyperparameter that I'm trying to tune. And it's a useful one, at least from the VC dimension perspective. It actually, in theory, it should do something. That's what this paper says.
Right. Okay. Yeah. So have you like done any? Okay. So for the papers, like I couldn't see any numerics, but are you planning to do like numerical verifications of your theories, or like are some other papers are working on that direction?
I've done it with students a few times to study overfitting and generalization here, and it I Yeah, we saw it happening. I forgot what the actual reason was, like 2 years ago. But yeah, we've seen in numerics that you could see this. But we haven't put it in the paper. It was just a student, I think, a bachelor thesis, undergraduate thesis.
Right, that's cool. And okay, so I think the question mainly from me. So like from here, right? Like I know from the literature, some people trying to replicate the double descent like structure from the deep learning to the like quantum neural network, right? But from here, you mainly make the assumptions on the typical like linear models that like typical like structural the standard like statistical learning theory stuff, the curve that we see, like the single descent one. What do you think about this one? As in, like, would you be able to even see the double descent curve from this kind of linear model? Because it's kind of clear to me that like in like this at least our current quantum machine learning model can only be written in a linear like model, in terms of linear model, so it shouldn't give us like the double descent like structures, right?
Yeah, that's a very let's answer first. I guess this theory here won't tell you anything about the double descent. This is let's say this is the early, let's say, structural risk minimization. So for people who are not informed, let's see where I have the picture here. It turns out, at least people postulate, that this plot here has a second part to it. Way down to the right, the red thing goes down again. It goes up, it goes up, it goes up, but at some point it goes down again. And that's sort of theorized by classical machine learning people to explain the success of neural networks, and it's often called over-parameterization. These bounds tell you nothing about over-parameterization in quantum models. These are just linear models indeed. And then the next question is, do you expect a double descent in quantum models because they are just linear? That's also a very good question. I don't know if the double descent or over-parameterization is an artifact of the nonlinearity in neural networks. I actually don't know if that has to do with each other.
Yeah, because like if we be able to convert all of the quantum machine learning model that we have in terms of linear models, then the non-linearity that we can get is only from the projection of the higher dimensional space back to the data space, right? And it's not the type of non-linearity that we can see from the neurons, like for example, sigma functions and stuff like that.
Do you need non-linearity to exhibit double descent? Is that clear? I don't know.
So I'm not too sure about the original double descent. But so far I haven't seen any kind of like quantum machine learning model that be able to show the double descent curve. And like for example, in this case, right, if your model be able to show double descent, that if you put k to very large, right, then you'll be able to see that the complexity and the training error kind of like be approaching to zero, right?
Yeah, but then you're just doing linear classification in an exponentially large space, and your generalization is just going to be bad. Don't do that, I guess, is the lesson. So there's no, I see what you mean. Yeah, there is indeed a limit to there, because you have the dimension of the feature space that you always run into and never go all the way there. I don't know. That's a very good question.
I know. Research fractions, right? One of the
I wouldn't also, it's big. Over-parameterization in quantum machine learning, it's still open. It's still very much, especially if you mean the same thing as people classically do, then that's a very interesting and open research that, that's something.
And you're, so like for this one, you based on your theory, you also propose the way to define the ansatz, right? And I saw one is basically the diagonalizing one. Right, the diagonalizing unit trees and
these blocks,
blocks diagonals one. As in like for this one is for me is kind of like highly related to the geometrical quantum machine learning, right? For geometrical quantum machine learning, they are trying to identify the subspace that have invariance.
Arguably, it's the different one. It's the last one. It's the symmetric preserving one. I would say is more to geometric stuff. That all has to do indeed with sort of being able to block diagonalize your unitary in these sort of in terms of the irreducible representations, and it is all due to the fact that the quantum state it produces have a certain symmetry, and this tells you about the size of the blocks, let's say. And if you're staying within one block, that's good because it's limited. And if you don't want the block to be too small, of course, but that's the symmetry preserving one is indeed very closely related to geometric deep learning stuff, although not quantified as such.
Right. Okay. Yeah. Got it. Okay. It seems like it's just mainly me shooting the questions. Okay. So like in your papers, right? I remember I also saw it in introduction as well as the conclusion. You're saying that like for some of the model, you the mapping between the like explicit models to the like implicit linear model basically break down. Like, could you evaluate on that one?
Sure. Yeah. So at the time there was this everything is a kernel model stuff happening. And the idea is that yeah, I think okay, so what is the good short explanation? So the power of a variational model, which yes, in the limit of expressivity would be representable by a kernel model. But the strong suit is that it is not in the limit of expressivity. The strong suit is that it parameterizes a submanifold of all possible observables. So that's the whole power. So yes, in the limit of expressivity, you might want to just do a kernel method, etc. But the power of the explicit model really lies in the fact that you're parameterizing a submanifold, or in this case, a subspace. Here I'm doing everything linearized. But a better bound here, or at least an improved bound, would be like how big is the manifold that I'm parameterizing, not just the linear space, because here I'm linearizing it and then therefore blowing up a dimension a bit. But the power really is in what is the manifold there, and restricted. And
I agree with you. I just want to like hear your kind of like explanation on that. Of course, like now we just want to limit our expressivities to the like problem that we want to solve. And then so that you have like better generalization errors, right? Just like the one that the work by Sofin, for example. He basically showed that like sometimes the explicit model will be outperforming the implicit model because
he gives very concrete examples of this, right?
But so that one is kind of like nice, and then eventually it's like all the works are linked, and then just like see how you kind of understand them and like kind of put the line between the right. Okay, maybe one last questions before we end. Recently I saw there was one papers publishing in PRA, like the papers of the name of the paper is like noisy quantum kernel machines, and over there they use the noise as the way to regularize the like the as a regularization parameters. And in that papers they're making use of the Riemann complexities to study how the noise will affect the generalization errors of the quantum models,
complexity,
right?
The complexity.
I'm just wondering like how, because over here you just consider all the perfect cases, right? I'm just wondering how noise will change the theories, or like in what part, like for example, or either the training errors or the complexity parts will kind of be affected by the noise.
Oh, that is a very good question. So I think one thing you can say is the bounds are combinable. You can sort of use both this theoretical and then put noise on top of it to sort of, in the ideal case, it would behave like this, and then noise on top of this. Yeah, it's weird because of course it doesn't become it's a channel then, and we are measuring an observable, which probably is also there will be. Okay, I think you're like combining linear classifiers at this point, right? You have ideal plus some error term. I think due to the.
As in, I actually found this explanation pretty cool. As in, like if we be able to separate the contribution from the noiseless case and the noise one, and then we know how the like noise will really play effect in like controlling the complexities, right?
But because if you do Gyurik cohering, you have like a little bit of the mixed added to your state, and then the trace is linear, so you have like a second term, and then you just have the ideal case plus some second observable, let's say distortion or error, and then it's a random. Oh, that's a random variable, and then perhaps it becomes something different.
So the main idea.
Yeah.
So the main idea from the paper is basically saying that basically your noise is kind of like if you have more noise in your system, basically you reduce the expressivity of the model per se, because it, like, for some model state it couldn't be distinguished, right? And then this like boost your generalization errors, and like there will be a like good sweeping point, like good point on the noise that you can good like complexities for having like low generalization errors and stuff like that.
Yeah, and that's one of the papers also references related work. I already studied the Rademacher complexity of the noisy case, and then indeed the noise parameter heavily influences this. But I just wouldn't know how noise would propagate through my bounds. Let's say that's not a priori very clear, because you're going to have indeed the second term and the sign, and then I think you're going to have the similar artifact. Similar bigger noise is less complexity, because indeed, as you say, you're not going to be able. The boundary just sort of becomes vague. You're less distinct. Your discriminative power is lower. So I think you would see the same, but I wouldn't know. That's my hypothesis is you would see the same behavior, but I wouldn't know how to do it as of quickly now.
As in, like, this will be the future where maybe people just like see, like in futures, like people might see, okay, I know how to add the noise, and then trying to use your work to improve to include noise, and then see how noise kind of like affects the VC dimension or the fat scattering and stuff like that, right?
Yeah, so that would actually be a nice question. Yeah, I like that.
Okay. Yeah. So I think it's now close to 5. Perhaps we can end our discussions and the presentation now. And thanks again, Casper, for your presentations. And I learned a lot from like your presentation as well as the discussion with you. And yeah, thank you very much for your time. Yeah. See you.
Cheers. See you.
Bye-bye.